We always hear in the news about international crises and negotiations lasting for decades, all because a certain country is trying to build a nuclear bomb. Iran is the closest example of this. Since the 1990s, we keep hearing that they are on the verge of having a nuclear weapon, and that they've already enriched uranium past 60%. But at the same time, they still don't have a bomb. This naturally begs an obvious question: why does this process take so incredibly long? If a country has an open budget, top-tier scientists, and natural resources, why can't they just build a nuclear weapon in a few months, or a few years? Secret lies in a weird term we hear all the time: uranium enrichment. What exactly is this process? And why does it take so much time? Welcome to Curious at Midnight. Before we begin, if you're new to the channel, don't forget to hit that subscribe button and ring the bell so you never miss our latest videos. The basic idea behind building a nuclear weapon relies on releasing a massive amount of energy from the core of an atom. To get to this atom, and make it ready for fission to create that terrifying explosion, we need a specific material with very rare properties. That material is uranium. By the way, uranium is not a rare material at all. It's found almost everywhere on Earth. Most rocks, riverbeds, and ocean floors contain uranium. That's why raw uranium is mined just like copper or iron. Once extracted, the rocks are crushed and ground into a powder. Then, specific chemicals are added to dissolve the uranium and separate it from the waste rock we don't need. The final product is a fine, yellow powder known as yellowcake. But here is the problem. The uranium we pull out of the ground isn't the kind that can just explode and create energy. The issue isn't the extraction, it's the processing. The uranium in yellowcake isn't just one type. It's a mix of chemical isotopes. The first isotope, uranium-238. This is a heavy, stable isotope. It's very hard to split or sustain a chain reaction. Simply put, it's totally useless for making a nuclear bomb. The second isotope, uranium-235. This is the lighter isotope that is highly fissile. This is exactly what every country is looking for, whether for a nuclear weapon or just to power a nuclear reactor. But the catch is that uranium-238 makes up about 99.3% of the entire mix. The uranium-235 that they actually want is a mere 0.7%. That is less than 1% of the raw ore. The challenge doesn't stop there. You might think, okay, we can just mine huge amounts of ore and extract that tiny percentage, and we'll eventually have a good amount. But the real challenge is separating these two isotopes from each other. We are not separating two different materials like salt and sugar, or oil and water. We are literally trying to separate the exact same material from itself. Both isotopes are identical in almost every way: same shape, same color, and same chemical properties. It is impossible to tell them apart. The only solitary difference between them is their infinitesimally small atomic weight. And even that weight difference isn't big. The mass difference between them is less than 1.5%. Yet, this is the one and only method we can use to separate them. This attempt at separation is exactly what takes so incredibly long, and it's the reason why uranium enrichment takes years. To separate the uranium isotopes, scientists use a method called a centrifuge. This is a way to separate materials using rapid spinning. Think of it like the spin cycle on your washing machine. It spins super fast, pushing the water out to the edges while the clothes stay in the middle. But the problem with applying a centrifuge to uranium is that uranium particles are solid. If you put them in a centrifuge, they will clump together, stick, and won't move. And even if you turn these particles into a liquid, the turbulence would cause the liquid molecules to mix right back together, making the separation extremely weak. Because of this, the perfect solution is to turn the uranium into a gas first. So, the first step in separation is changing the state of the material itself. The yellowcake goes through a series of complex chemical reactions until it becomes a gas called uranium hexafluoride. This gas is the magic key to the enrichment process, but at the same time, it is a chemical nightmare for anyone handling it. It is highly toxic and fiercely corrosive. If it touches almost any metal, it eats through it immediately. That's why handling this gas takes extreme caution and time. First, you have to build an entire network of pipes, pumps, and valves made from specially designed, corrosion-resistant alloys. Once the gas is ready, it enters the centrifuge stage for separation. After turning the uranium into a gas and sealing it in these special pipes, it is fed into tall cylinders that start spinning at insane speeds, reaching up to 100,000 revolutions per minute. That is almost 3 times the speed of sound. We do this to take advantage of that tiny weight difference we talked about between the 238 and the 235. When the cylinders spin at these massive speeds, the heavier uranium-238 is forced against the outer wall of the cylinder, while the lighter uranium-235 stays closer to the center. Are we done? Not yet. The uranium-235 in the center still isn't pure. It still has some 238 stuck to it. After all of this effort, the concentration of uranium-235 only goes up from 1% to maybe 2%. So, the gas on the outer edges is extracted and thrown away or recycled, and the gas in the middle, which now has a slightly higher percentage of 235, is fed into the next centrifuge. This process is repeated thousands of times, without exaggeration. There is a massive network of centrifuges all connected together. Each machine raises the percentage of uranium-235 just a tiny bit before passing it to the next one. It is a slow, difficult, dangerous, and tedious process. That is why it takes years. And this entire operation is what we call uranium enrichment. Now that we understand how enrichment works, we need to understand what enrichment actually is. Enrichment has different grades and levels. The percentage of uranium-235 in the mix, which is essentially the enrichment level, needs to reach a specific number depending on the final use. If a country is enriching uranium to fuel a nuclear power plant to generate electricity, it only needs an enrichment level between 3% and 5%. If the goal is to power medical and scientific research reactors, the required level is around 20%. But if the goal is to build a destructive nuclear weapon, the percentage needs to cross 90%. This is called highly enriched uranium, or weapons-grade uranium. But here is a crucial point. The effort and time required for enrichment are not distributed evenly. For example, it doesn't take 20 months to go from 1% to 20%, and then 70 months to go from 20% to 90%. The reality is that raising the enrichment level to 20% takes about 90% of the total time, effort, and energy required to build a nuclear bomb. The remaining 70% jump to weapons grade takes significantly less time. This is because the volume of material being processed at that stage is much smaller, and the impurities are almost gone. That's why when a country reaches 20% enrichment, the international community panics. It means the remaining time to reach bomb grade is just a matter of weeks, or a few short months. Of course, there are other factors that can change this timeline, like the infrastructure, the resources needed to run the facility, and the level of secrecy, because many countries try to do this entirely under the radar. This brings up the next question. If we assume a country overcomes all these hurdles and finally gets its hands on 90% enriched uranium, does that mean the country now has a nuclear weapon? The answer is absolutely not. Enrichment is simply providing the raw fissile material. Turning that material into a weapon is a completely different story that takes additional years of highly classified research and testing. The enriched uranium has to be machined and cast into a sphere-like mass. This sphere becomes the core of the nuclear bomb, and handling it requires highly specialized labs for radiation protection. What's even harder is designing the detonation mechanism itself. Uranium doesn't just explode like gunpowder. You can't just light a match and watch it blow up. When uranium-235 reaches critical mass and is struck by a neutron, its nucleus splits, releasing a massive amount of energy, plus more neutrons. These neutrons then strike other atoms, creating a rapid chain reaction of explosions. And all of them must detonate at the exact same fraction of a millisecond to create a true nuclear explosion. If we look at reality, America is considered the fastest country in history to build a nuclear bomb. The Manhattan Project seriously began in 1942, and they reached their first successful test detonation by July 1945. That means it only took them 3 years. The reason they got there so fast was World War II. The project had an unlimited budget and a massive industrial effort behind it because the whole world was terrified of the Germans getting it first. The greatest minds in physics were in America at the time, even if they weren't originally American. So, it wasn't just America building the bomb, it was a collective effort from the brightest minds around the globe. Starting with Albert Einstein, who sent a letter to President Roosevelt warning him of the German plans for a nuclear weapon, to Niels Bohr, one of the brightest scientists in the field, to J. Robert Oppenheimer, the director of the project, and Enrico Fermi, among many others. More than 130,000 people worked on the project with a budget exceeding $2 billion at the time, so their speed wasn't exactly surprising. Even the Soviet Union, which followed right after them, managed to detonate a bomb after about 6 years of work. But it's widely believed that their spies fed them highly sensitive information from the original Manhattan Project, meaning, they weren't starting from scratch. Finally, there is one more thing we need to clarify. Uranium-235 isn't the only element used to make nuclear weapons. There is another element, Plutonium-239. The difference is that plutonium is not a naturally occurring material. It is manufactured inside nuclear reactors themselves, extracted from the uranium-238 that we said we didn't use. And the big difference? Plutonium doesn't require enrichment in centrifuges. It only needs chemical separation. But the problem is that separating it is incredibly difficult and dangerous because its radiation is terrifyingly powerful and requires highly advanced shielding technology. During the Manhattan Project in the US, they actually used both materials because they weren't sure which one would work. The little boy bomb dropped on Hiroshima was uranium, but the fat man bomb dropped on Nagasaki was plutonium. And when the Soviet Union wanted to speed up their nuclear program, they chose plutonium and copied the American design because it was a safer bet for them than waiting on uranium enrichment. And that's a wrap. Who made it this far? If you're still watching, you guys are absolute legends. Smash that like button before you leave so we know how many of you watched until the very end. And don't forget, if you have a late night thought keeping you awake, drop it in the comments below so we can answer it in a future video. Peace.